Uh, Thank you, Yoram and Yoav. Actually, I once gave a plenary lecture in the information theory conference, and one thing that impressed me about this conference is that whenever a speaker was presented, they first presented the one who is going to present him. So this is more or less what happened now. This is what. So it's really a great pleasure to be here. Thanks for the invitation, and thank you all for coming. I'm really impressed with the number, and I hope you'll not be disappointed. And I should say right at the beginning that I'm not an engineer, although some of my best friends are. And although I did study, my first degree is from the Technion, mathematics. I see here at least one teacher of mine from that period. And since I'm really a mathematician, what I'll talk about are applications of discrete mathematics, graph theory, and combinatorics in problems in communication. And I chose two relatively recent examples, one recent, one very recent. And in both of them, I think the combinatorial problems are interesting and actually are still somewhat open. So we know something about them, but we still don't fully understand them. So let me just start by saying as an introduction that questions and methods and techniques from discrete mathematics and graph theory play a crucial role in information theory. And there are many examples, especially in what's called the zero-error information theory. And I wrote here a few topics that I will not talk about, but these are topics that I like. So the Shannon capacity of graphs, Witzenhausen rate of channels, index coding. There are many other examples. A lot of zero-error information theory really has to do with combinatorics. But today, I'll mostly speak about examples that have to do with communication networks, and I think again the problems are interesting, and maybe the methods are. So here is the first example I'll discuss will be what I call delay coloring in optical networks, and you see here a picture illustrating it. You know that nowadays when you prepare a PowerPoint presentation and you need a picture for something, then you go to Google Images or Bing Images and you type delay coloring and optical networks, and this is what you get. So I have no idea what exactly this is, but maybe it's all right. So this is OK. So here is the problem. I think it's interesting. So consider the following model. And this was motivated by the study of optical networks. And these are some papers that had to do with it. Specifically, I heard about it from Huxell, Wilfong, and Winkler. They were all, at that time, they were all in Lucent Technologies. So Huxell was visiting, and Wilfong and Winkler were there. Both of them are not there anymore. I'm not sure if it says something about the problem, but I think it's a nice problem. So consider the following communication network. So it will contain a set A of red transmitters. So I'll always denote the transmitters by red, and a set B of blue receivers. And each one of the transmitters has some set of messages that are addressed to some of the receivers. All the messages are distinct, let's say. And it could be, so every single message, let's think about it, that they all are of the same length. But it could be that the transmitter has to send more than one message to the same receiver. So if a message is longer, then you can think about it as 10 distinct messages that he has to send to this receiver. And And somehow the technology is such that every message has some associated delay. And it's good to think about it that this will really model the time it takes the message to reach its destination. Okay. And time is discrete and synchronous, so we have these time units. And what we want is we want to find a minimum length periodic setup that will enable me to send all the messages so that every transmitter will send at most one message in any time unit, and every receiver will get at most one message in every time unit. And we should do it again and again. So we want that in one period, everybody will be able to get the messages that it's supposed to get. So let's see what this says formally in terms of a graph problem. Maybe first I had some example here. So these are, on the left, you see this red, somewhat red, if you want, transmitters. And we have these blue receivers on the right. And then we have the delays. So in every message is represented by an edge here. And the delay tells me what is the delay of this message. And what I could do here is that I could fit it all in a period of size 3. And here is the example. So in time unit number 2, I'll send this top message, and it will reach the receiver in time 3. Right? And then this other message, I can send it in time number 1. And because the delay is 2, it will reach the second receiver in time 3. And here this is 2 and 1, and this is 1 and 1. You see, I'm computing things modulo 3 because this is a periodic setup. So I want to know how things behave modulo 3, and because of this 2 plus 2 is 1. And you see that the important thing here is that the schedule is such that when you look at the bottom receiver, then the 3 distinct messages that it gets it in distinct time units. So indeed, it will be able to hear all of them. All right. So this is a question, and if we try to model it formally, this is what it will say, and this will be similar to some problems about graph coloring. So we have a bipartite multigraph. So multigraph will mean that we could have parallel edges that connect the same pair of vertices. The bipartite graph, it means it has 2 sets of vertices, the red set of the transmitters and the blue set of the receivers. And every message is represented now by an edge. Okay. So the edges, as is written here, represent the messages. And there is a delay C of E for every edge E. So for every edge E, we have some number that will tell us what delay it takes. And what we want is we want to find a smallest possible integer k. So this will be the size of this periodic setup. So that there is an edge coloring of the edges by numbers from 0 up to k. Actually, I should have written k minus 1, but never mind. So I want to think about the integers modulo k. So this coloring will tell me in which time unit I'm sending every message represented by an edge. And what is the conditions that we have to satisfy? If we have 2 edges, E and E prime, that share the same end in the left side, in the side A of the transmitters, then the F values of them should be distinct, right? Because they have to be transmitted in different time slots. We said that in every time slot, a transmitter can transmit at most 1 message. Okay, so they have to be distinct. And on the other end, if 2 edges have a common point in the receiver side, in the other side, then what has to happen is that if we compute the F of the first edge, namely the time in which it is transmitted, plus the delay, then modulo k, it has to be different than the F of the second edge plus its delay, right? Because this will mean that the 2 messages reach the same destination in distinct time units modulo k. And what we want is to find this smallest possible k. And we can consider the algorithmic problem, but let me what these guys wanted actually is to consider the extremal problem. So how small can k be? Okay, so hopefully the model is makes sense. And one obvious fact is that the number of time units, this k, has to be at least the maximum degree of the graph D, right? Because if some transmitter has to transmit D distinct messages, then I need at least D slots. And the same thing, if a receiver has to receive at least D distinct messages, then again I need at least D distinct slots. So this k has to be at least the maximum degree D. And in fact, if all the delays are equal, or equal to 0, or equal to any numbers that you want, then it's easy to see that what we really need is we just need to find what is usually called an edge coloring of this graph, a proper edge coloring. Namely, the function just has to assign to any two incident edges distinct values. Because if they are distinct, they will be distinct also after I add the same delay to all of them. So this is called edge coloring, and a classical simple theorem of Hall and Koenig, actually proved also by Frobenius earlier, says that essentially this easy or obvious lower bound is also an upper bound. Namely, k equals D is always sufficient. If we have a bipartite graph, even with parallel edges, if the maximum degree is D, we can color all the edges by D colors so that adjacent edges get distinct colors. Okay, so but we have delays, right? And the delays maybe are different. So here are two conjectures. So the first conjecture was in this the first papers that I mentioned by Ross et al. And they conjectured that always D plus little o of D. So now we think about D as a pretty big number, maybe 1,000, I don't know. So what the conjecture is that we don't need much more than D. We can always find the coloring, even when we have delays, where k will be just D plus a little bit, a small error term. And the second conjecture is even bolder, so that's by the second group, by Huxell, Wilfong, and Winkler. And what they thought is that D plus 1 time slots always suffice. It is easy to give examples where you need at least D plus 1, because if, for example, all the delays are 0, so even if we have just two vertices with D parallel edges between them, and all delays are 0 besides one delay that is 1, then it is clear that k equals D will not be enough, because k equals D will mean that I give a permutation of the numbers from 0 up to D minus 1, or from 1 up to D, to these edges. But then if we add 1 to one of them, then 2 will be equal. All right, so sometimes we need D plus 1. And what I thought is that D plus 1 always suffice. And in fact, this is not obvious even for the case of D parallel edges. So just the simplest networks that you can think about, just one transmitter, one receiver, D parallel edges, but distinct general delays on the messages, then you still have to prove something. And that's actually equivalent to a theorem, an old theorem of another Hall. So the top Hall is Philip Hall, and this one is Marshall Hall. And he actually proved something that is more or less equivalent to saying that for D parallel edges, then D plus 1 indeed suffices. So even this is not so simple. And actually, both these conjectures, as they stand, are still open, but I want to tell you something about it. So here are two things that we proved a few years ago with A+Asodi, who was a student at the time. So it says the following. So the first conjecture, it holds for simple bipartite graphs, namely, if we don't have parallel edges, if every transmitter, it has to send to every receiver at most one message. I don't want to have, right? So all the messages are of the same length. And if a transmitter has to send many messages, then it's to distinct receivers and vice versa. Okay? So if this is the case, then indeed we don't need much more than d. So something like d plus some error term, maybe it's something that behaves like d to the 2/3 or so, this is what comes from the proof, will always be enough. Okay? So this is the first thing. And the second, about which I'll say something, is that the second conjecture, this d+1, holds in some cases. And I wrote here for planar multigraph satisfying some technical condition. Let me just say some specific case, because I want to mention something about the proof for that. So we said that it's not very simple even for d parallel edges. Here is something that is somewhat more general. So think about any even cycle, okay? But now you can take parallel edges as you wish. So every edge of the cycle, just duplicate it as many times as you want. So not necessarily the same number of times. That will define somehow the maximum degree. Well, for, maybe I didn't write it here, but OK. So yeah, it's written here. So let me assume also, although there are ways to get around it, let's assume also that the maximum degree is such that d+1 happens to be a prime number. Okay. So if it's a prime, then this d+1 time units suffice. So this is a statement. And I just, so I'll not say much about proofs here. Maybe I'll describe a little bit of the idea of the proof of theorem too. But let me, and what I like to say is that I want to kind of describe enough to give you the impression that if I would have had 10 more minutes, then you would have been able to follow, which is more or less true. But this is, let's just say that the proof of the first theorem, about which I will really not talk, this d plus d of d is probabilistic, and it uses something so techniques that have been used in something that is called least coloring of graphs, and specifically there are results by Kahn, by Hegvist and Janssen, by Molo and Reed, by others as well. So somehow there is something called the semi-random method, and somehow it enables us to get this result, that we don't need much more than the maximum degree. And the proof of the second theorem is very different, and it's algebraic, and uses some basic properties of polynomials of many variables, of multivariate polynomials. So this is something that I called some years ago combinatorial Nullstellensatz. It's an example of this. I want to say a little bit about this. As I said, not much. So here is a hint about this algebraic proof. So again, we have this bipartite multigraph. Maybe it's planar, but think about it now as a general multigraph. The maximum degree is d, and I have these delays, and I want to find this coloring using d+1 colors, or d+1 time slots. So the first thing, so as I said, it's convenient to assume that this k, the number of time slots that I use, let me assume for now that it's prime. As I said, there are ways to get around this, but this will require to use multiplication in terms of, instead of additive. So somehow it's convenient to, let's think that it's a prime, okay? Because this is good enough to understand the basic idea. And now what I wrote here is something very simple, which just says that I can encode this problem in terms of some polynomial of many variables. Namely, for every edge E, I'll have some variable x sub E. This will get values in z modulo k, which is a prime, so that's a field. And xe will tell me in which time unit I'm going to send the message that appears on edge E, on the edge E. Okay. Now what I want, remember what we said, is that if two edges have a common point in A, in the transmitter side, then we want that they will not be sent in the same time unit. And therefore, I write there a product of the differences between them over all edges, over all pairs of edges that have a common point in the left side, because if this difference is non-zero, then it just means that they are distinct. Okay, and I do the same for the right side. For the right side, I go over all pairs of edges that have a common point in the right side, and now I take xe plus the delay, c of e, which has to be distinct from x of e prime plus the delay of this e prime, because that will mean that they didn't arrive in the same time. And if all this big product over all pairs of incident edges happens to be non-zero for some assignment of values of zk, then we found a good assignment. So somehow we just have to show that there is a way of finding values for these variables for which this is non-zero. And basically what this says is that it says that this polynomial is not identically zero. So somehow we have to show that some coefficient of this polynomial is not identically zero. And in particular, what I wrote here is that if this graph happens to be a d-regular planar multigraph, so all the degrees are exactly d, and it's planar, we can draw it in the plane with no edges crossing each other, then it turns out that one can interpret some coefficient, and the specific coefficient is what I wrote here, the product over all the variables of x of this variable raised to the power d minus 1. So this coefficient, the coefficient of this monomial, will be exactly the number of proper edge colorings of the multigraph by k colors. Namely, the number of ways of coloring this multigraph, the edges, by k colors, so that adjacent edges get distinct colors. So this is not an obvious thing, but somehow this can be shown that indeed this coefficient can be interpreted combinatorially. And again, it turns out that in some cases, this enables us to show that this coefficient is non-zero modulo p. We have to be non-zero in the field we are working in. And for example, this is not too difficult to do if the graph was an even cycle in which some edges were duplicated. And if we did this, then the polynomial, this coefficient will not be zero, and therefore the polynomial does not vanish, and therefore we can find these x sub e's. So that's basically the idea, and with this I'll leave it. Note, by the way, maybe I'll mention it at the end, but note that this does not tell me how to actually find such a coloring. So if I really want to do it, I'll have to give a schedule to tell each message when it is supposed to be transmitted. So we have this algebraic proof that tells us that there is this way of finding values for the x sub e's so that all this product is non-zero, namely everything is OK. But this is because of some manipulations with polynomials. It's not clear how we can now efficiently find all these values x sub e. Okay. So let me leave this and go to the second half, maybe a little bit longer will be the second half. So that's something different. Namely, if you lost me, you can start listening again. You don't have to, you can, but it's a okay. So here's that's very recent, and here the title is Induced Matchings and Shared Communication Channels. And what I want to do now, and maybe I should apologize for it in advance, but so what I want is actually to start with the combinatorial problem, with the mathematical problem, that will look a little bit obscure, I must admit, at the beginning, but believe me, so at the end I'll tell you why indeed, or I'll show you where it comes from some problem in communication. So, but I want to first talk about induced matchings in graphs. Okay, so we start again from the beginning, and here you see that I really don't assume anything because I wrote the definition of a graph even. So a graph is an ordered pair, just to see the notation. V will be always a set of vertices. Our graphs will be finite. E will be the set of edges. And you see here an example of a graph. Okay, so you know what a graph is. Now, what is an induced matching in a graph? So here is a graph. An induced matching is first a matching. So a matching is just a set of isolated edges. So it's a set of edges like the red edges that you see here, no two of which share a common point. Okay? So here this red form a matching. They don't share a common point. It's also an induced matching in the sense that there is no other edge that besides the red edges that connects two endpoints of these red edges. Namely, if we look at the induced subgraph on all the vertices that are saturated by the red edges, then we don't see there any other edges but the red ones. So this one is an induced matching, whereas if I would have chosen, I don't know, that edge and this edge, then it would not have been induced because this edge will be an additional one connecting them. I was told that I should stand close to here so that the picture will look good. So I'll try not to go there too often. But OK, so this is an induced matching. And here is the extremal problem we want to consider, which, as I admitted, may look somewhat obscure at the beginning, but it's actually an interesting problem that arises in several situations. And I'll tell you in passing just a little bit about others, and then I'll show some communication problem where it arises. So what I want to know is how dense can a graph be? Can we have many edges so that still all this graph is a disjoint union of large pairwise disjoint induced matching? So here you see an example of a graph. This graph, that's a graph of the three-dimensional cube, but doesn't matter. So that's a graph on 8 vertices with 12 edges, somewhat dense. I don't know. I mean, we will be interested in big numbers. But and I wrote it here as a disjoint union. I wrote the edges of induced matchings, each of size 2, which is somewhat big. Maybe we want much bigger. And you see that we have here all these, like the red matching is an induced matching, the green matching is an induced matching, and so on. And I want to know how dense can such a graph be. And some of the logic is, and I'll say something about it later also, that if the matchings are very big, then it's hard for the graph to contain very many edges, you see, because whenever we have some big matching, because it's induced, there are lots and lots of missing edges. All the other pairs, connecting pairs of vertices of this induced matching are missing, right? So somehow, if the matchings are big, it will be hard to be very dense. And so what do we know about this? Here is some old result of Ruja and Semeredy. What it says is that if G is a graph on n vertices, and it is the edge disjoint union of induced matchings, each of linear size, so pretty big, let's say n over 10 or n over 100, let's say n over 10, then the number of these matchings is only little o of n. So the total number of edges of the graph will be only little o n times n over 10, so it will be little o of n squared. Namely, maybe it can be somewhat dense, but not very dense. We cannot contain 5% of the total number of possible edges. Okay. Now, how little is this little o n? So what their proof gives is only it's somewhat little. Namely, it's some constant times the 5th root of log star of n. Log star of n is how many times you have to take log from n before you reach 1. Let's say, or something, which is at most 1. So maybe log star of the number of atoms in the universe is 4 or 5, maybe, I don't know. But then you have to take the 5th root. OK, so, but still, formally, this little o of n. Somehow, OK, actually, this has been improved by quite a lot recently by Fox. And what he proved is that this little o of n is only n over log, 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 log n. And you take log 1 over c times, where c is I mean, this also looks not so impressive, but it's still much, much better than the log star to the 1 over 5. Still, I think for the number of atoms in the universe, it will still be 2 or 3. But anyway. But formally, this little often. OK. And as I said, just in passing, I wanted to mention that some of this Ruja-Semeredy result is natural. And here are 2 places where it appears. So one thing, this was the original motivation of Semeredy when he proved what is called the regularity lemma, which somehow comes in the proof of that. So this can be used to show that any subset of the integers modulo n, say, or any other abelian group of odd order that does not contain a 3-term arithmetic progression, any such subset is of size little of n. So that follows from what I said before, just in a few lines. So that's easy. These are other proofs of this statement as well. The initial proof was by Roth in the 50s, but anyway. So and also I want to mention that that this, together with some construction, old construction of Behrend from the 40s, it has some application in what is called graph property testing, which again, I just wanted to mention the buzzword. I don't want to talk about this, just to say that this is related to something. OK. But what I want to talk is a case of even much more dense graphs. So I want to really hope that I'll be able to cover by induced matchings graphs that are nearly complete. OK, so let's talk about these. So again, remember that the question was how dense can a graph be if its set of edges is a disjoint union of large pairwise disjoint induced matching? And just repeating what I said, this Rouja-Semerdy result plus this construction of Behrend, they basically say the following, that if the graph has n vertices and every matching is of size some constant n, n over 10, n over 100, the total number of matchings is only little of n, that's what I mentioned before. But on the other hand, if the matchings are somewhat smaller, so each of them is of size n to the 1 minus little 1, so still pretty big, n to the 0.99, let's say, then in fact we can have about n matchings. Still, the product will not be very dense, the total number of edges, but it's OK. So I still want to consider this question. So just again to think about the problem, just to understand to kind of digest the definition, let's realize something very simple. So if the graph has n vertices and each matching contains more than n over 3 edges, right? So I have really, the matchings now are very, very big. Each of them covers more than 2/3 of all the vertices. If this is the case, then I claim that we cannot have even 2 disjoint induced matchings, because you see the first matching will cover more than 2/3 of the vertices. So the second matching that is of the same size, at least one edge of it must contain 2 vertices that are covered already by the first one, because otherwise each edge of the second matching must contain an uncovered vertex, but we don't have enough of them. Again, it's not so we can have only one if they are really big. Now, if they are somewhat big, if they are a little bit bigger than a quarter n, then there is also a simple argument that shows that the number of matchings is only a constant depending on epsilon. That uses one of the easy bounds from coding theory. But and in general, just again to try to convince you that the intuition suggests that we cannot have very dense graphs. In general, we think that if the matchings are large, so here you see an example of a pretty large matching, then the graph cannot be dense. This is how it seems, because again, if we have this big matching here, then there are all these other pairs. These are all missing edges, right? We cannot have any of these edges. So whenever I have one big matching, there are lots and lots of missing edges. And therefore, it seems that I'll not be able to squeeze enough big matchings here, because again, I'm not allowed to use all these matching edges. Okay? And specifically, actually, this intuition is very convincing. And in fact, there was a specific conjecture by Roy Meshulam from here, who says that, which says that we cannot have what he thought, and I think it's very intuitive, that we cannot have a graph on n vertices and constant n square edges, so even n square over 100, let's say, like 2% of the total possible number of edges, that will be of matchings, each of size at least n to the epsilon. Right? So if we want the matchings to be somewhat big, just some small power, then the graph cannot be very dense. And I think that's natural. So I was trying to convince you that it's natural to think that this is a case. But actually, this is very false. So So all this kind of convince you that not only Roy should be a surprise, but you should be surprised as well, because it says that it's more or less as false as it can be. So this is something we did recently with Ankur Moitra and Benny Sudakov. We showed that you could have graphs on n vertices which contain almost, so think again about n is large. So they are nearly complete. Almost all the pairs are connected. So they have 1 minus molecular 1, n choose 2 edges. Say 0.999, n choose 2 edges. Almost every pair, 99% of the pairs are connected. And still, they will be the edge disjoint union of match. Each of them will be of size at least, not n to the epsilon, but actually n to the 1 minus little 1. So it will be really big. Right? So somehow what this says is that you can have an almost complete graph that is the edge disjoint union of almost perfect, almost complete induced matchings. Right? Of course, if it's complete graph, then it cannot have an induced matching even of size 2, but it's almost complete. And the matchings are of size, well, n to the 0.999. Okay? So this is, and there is a second statement which is related, and actually maybe we want to use this one, is that that also if you fix some epsilon, so think about epsilon as a small positive real, then we can cover the complete graph on n vertices. Now we can cover all of it by some C of epsilon graph. So maybe if epsilon is 1 over 10, then maybe we need 100 graphs. Okay, so we'll have some constant number of graphs, and we'll be able to cover all the complete graph. And each of the graphs that we use, this GI, each of them we will be able to cover it by a very small number of induced matchings, n to the 1 plus epsilon. Namely, each induced matching in it, in the graph GI, will be of size n to the 1 minus epsilon roughly. So it will be very big. Okay. And I'll say I wrote here something on about the proof, but it just so somehow so the proof is geometric. At least the basic constructions. There are two constructions. One uses more ideas from coding theory, and one is more geometric. So it uses some geometric construction. It's based on some high deviation inequalities. So what's called measure concentration in high dimensional Euclidean spaces. And then there is some probability and some ideas from coding theory. And I mean, yeah, and it's so again, so maybe I would just say that if I would have had 10 minutes more, then I would have written some sketch here on the blackboard of something, but probably this would not have been so useful anyway. So let me not do it. But the construction is pretty simple. So if you just, I think it's still very surprising that this graphs exist. But what I want is to tell you why this is relevant to some problem, and here is a so let's talk about some model of shared communication channels, and I'll tell you something about this. So we want to consider this has been considered before, as I'll mention soon. So a shared channel will consist of n sources Si, and again my sources will be red, and n destinations Tj, they will be blue. Okay, and the sources Si, so each source Si has to transmit message Mij to destination Tj. Let's assume that each one has to send some message to each other one, and all the messages are distinct. Okay, so all the and how do we do this? So this will be implemented, the model that we consider is that this will be implemented by constructing several interconnection networks G sub p between the sources and the destinations. So what will be every interconnection network? It will be a bipartite graph with vertex classes, the sources on the left. These are the red transmitters, and the destinations on the right. These are the blue receivers. And there is some connection between them. And the model is what is sometimes called the radio model. So, so a message if I'm in a interconnection network G sub P, then a message that is sent by SI, it reaches all the destinations TJs that are connected to it. Okay, so this makes sense somehow. Okay, and on the other hand, a message Mij is received successfully by TJ, namely he can hear something, what's going on, in a given time unit, so in a given round. If it is being sent by SI first, it has to be sent. And also, no other source connected to TJ transmits in the same round. Because if someone else connected to him transmits in the same round, then he will get two messages simultaneously, and they will somehow garble each other, and will not be able to recover it. Okay. So because of this, and we'll see a picture soon, the set of messages Mij's that are received successfully in a given round, it forms an induced matching in the graph GP. Okay, let's see it in a picture here. So again, we have these transmitters on the left, receivers on the right. And what I'm saying is that you see that here the two red edges that you see here form an induced matching in this graph. Namely, they are a matching, and there are no other edges of this graph that connect two of their endpoints. And indeed, this means that we can send these two messages in this graph. So now we have this graph where all the edges you see here are the connections. Okay? And if we just tell the two bottom transmitters to send their messages, right, the corresponding messages, so they will send it. And these two middle receivers, this guy and this guy, will listen, and they will be able to hear it because nothing interferes with it. But on the other hand, here is another example. So if we would have tried to send these two messages that appear in red here, which do not form an induced matching, right? Because here we have this extra edge that that connects their two endpoints, right? You see, well, you already noticed by now, because we are close to the end of the lectures, that my PowerPoint skills are very limited. So this is the only place you'll see something moving. So let me do it again. So here it is. Okay, so you see that the red messages here, we cannot really send them in one time unit, because if indeed the transmitter number 2 from the top and transmitter number 4 from the top send their messages, then this guy, right, so this will get both of them, and therefore he will not hear what he has to. Okay, so indeed, what we can do in one time unit is indeed an induced matching. Okay, so because of this, the objective, since we have all these edges from all the sources to all the destinations, the objective is to cover the complete bipartite graph. We have to cover altogether all the edges, the complete bipartite graph with n vertices in each class. And we have to do it by a small number R of graphs GP. Each of them is one of our interconnection networks, so that each GP can be covered by a small number of induced matchings, because this small number will be the number of rounds of time slots that I need for this interconnection network. And the obvious bound here, what we can do is that obviously for every R, even for R equals 1, so if we just take the whole graph by itself, then the total number of required induced matchings is not more than n square. There are n square messages altogether, n square edges. So we can just allocate one time slot to each of them and just send it one by one, right? So this we can do always. But in fact, for every R, the total number of induced matchings is also at least n. And this is because, say, one transmitter altogether has to send n distinct messages. And this has to happen in n distinct time units. So we are between n squared and n. And the question is if we can do something. And this is OK, and I wrote here that the lower bound can be slightly improved. Let's not worry about this. So in fact, this question was asked by Birk, Lineal, and Meshulam. So at least Tzach is in the audience here. some 20 years ago, right? Yeah, this is another effect that you kind of learn as years pass, that all the things that you think that happened 2 years ago actually happened 20 years ago. But this is all right. Right. So what they showed, they had some constructions. That is some clever constructions. It does better than the trivial bounds that I mentioned to you. And indeed, for our graphs, what they could get is that the total number of required induced matchings will be at most n squared divided by some log power, log n to the r minus 1. So if r is 2, for example, you would be able to do it by n squared over log n. So this is some, OK. And actually, this new thing, because I told you that we can have these nearly complete graphs that can be covered by very big induced matchings, and also we can cover all the edges of the complete graph by a small number of graphs so that each of them can be covered by a small number of induced matchings. So if you substitute in it, this will tell us that for our graphs, actually, the total number of required induced matchings will be at most n raised to the power 1 plus a little bit, plus some constant 1 over log r. So really, it will reach, we said that the obvious lower bound is n. It will be close to n, or it will be n to the 1 plus epsilon for fixed r that is big enough. And even for r equals 2, for r equals 1, it's trivial that we cannot do anything. We need n squared. But for r equals 2, if we just have 2 interconnection networks, so we cover it, then if you kind of optimize the parameters, then you can make sure that the total number of required induced matchings will be at most n to the roughly 1.94. I told you that really both problems I was talking about are not completely solved. The lower bound here is only n to the 4/3. That's an easy lower bound. And the upper bound is this. So it is some power of n. It's not clear what is indeed the truth. But at least you can get the power of n already for r equals 2. So let me just finish with a few problems. I basically mentioned them, but I'll kind of mention them again or stress them. So the first conjecture that I mentioned in the first half of the lecture was that by Huxell, Wilfong, and Winkler, is that every communication network with delays in maximum degree d admits a periodic schedule of length d plus 1. As I said, we know only very special cases of this. Still examples suggest that this is true. I think it is true for d equals at most 3. So this is still true, but I don't know what happens for bigger d. There is this related problem that I told you that there are some results there. So for example, d plus little od is enough if the graphs are simple. And there was this algebraic approach that tells you that in some cases d plus 1 is enough. Then there is still the algorithmic question. How do we actually find these schedules? So we will know that such a schedule indeed exists because of these manipulations with polynomials and because some coefficient is non-zero. It's not clear how to actually find it in, say, polynomial or efficient. And somehow, so this is a specific case of polynomial. It's not too difficult to show that the general problem, if you have a polynomial and somehow you know there is a way to convince you, so I can make this precise, there is a precise way to convince you quickly that some coefficient of this polynomial is non-zero, and because of this you will know that there is an assignment that you can find so that the polynomial is non-zero, and then the algorithm question is to find such an assignment. This is probably a hard problem in the sense that if we would know to solve it for any nicely given polynomial, then we would be able to invert some one-way functions. So we would be able to break some cryptographic protocols. It seems that the general problem of this type is difficult, but here the polynomial is a specific polynomial. Maybe we can do it efficiently, or maybe we can use some other argument to do it. And the other thing is this improved bound for the induced matching problem. So what I said is that we kind of understand what's going on, at least in some range of the parameters. But again, the general problem is for each given n and t, we want to estimate the maximum possible density of a graph on n vertices, which is a disjoint union of induced matchings, each of size t. Right? So that's a very easy to state question. And because of this other connection that I mentioned in passing, if we get very good bounds for this, for general n and t, it may supply improved bounds for the maximum density of subsets of 1 up to n with no 3-term theoretic progression. So again, this is a question that, although it may look artificial if you haven't thought about it, is a question on which people really worked a lot, and there are results starting with Roth, and then by Semeredy, and by Bourgain, by Gowers, and the record now is by Tom Sanders, and somehow there is still a very big gap between the upper bound known there and the lower bound. So it will be nice to understand it better. And it will say also something about graph property testing, but I didn't talk about this. And it may provide also better constructions for these shared communication channels. And with this, let me finish, and thank you for your patience.
Okay, so what we're going to have now is a discussion, but people are free to leave now. So we've got another 15 minutes of questions, and we'll do it this way. So thanks a lot for Noga.
Okay, thanks, yeah.
And everybody who is interested can stay.
אוקיי, כן. כן, כי לרוב השאלות זה הרבה פעמים מאוד מביך ששואלים. אני רק רוצה לדעת אם הוא באמת בסוף שינה לי משהו, כי הוא איכשהו, כי אני מפחד שיהיה לי, אבל אוקיי.
יש עכשיו דיון, מי שרוצה לשאול שאלות,
אבל בסדר, לא...
ולשמוע שאלות.
אוקיי, נצא מתוך הנחה שהוא לא שינה לי שום דבר שיגרום לי לצרות בהמשך. אז זה מדהים מספר האנשים שמגיע לפה, אני לא... כן, אוקיי, ויש גם... כן, היי.
בוא נתחיל.
להישאר עם המיקרו? לא, נראה לי שלא.
טוב, מה שאנחנו עושים עכשיו, עכשיו זה הזמן לשאלות. אוקיי, מי שנשאר פה. ומתי הבחירה אחרי השאלות? עכשיו הזמן למי שרוצה לשאול שאלות. מה? חייב לשאול? לא, הוא יכול להקשיב לשאלות.
אני מוריד גם את המיקרופון, אז זה יהיה, כי נראה לי שאין פה הרבה אנשים, יכולים להתקרב, זה יהיה יותר...
צחי.
אני לא יודע, אין לנו, we don't have any reason to speak English now, we don't, or...
Anybody here speaking? You're an English speaker? Good, so we'll do it in English.
So we have, okay, very good.
Noga, can you turn on the presentation or is it dead already?
I can, I think it's a solid state, so it's supposed to be fast. But although I never, but then the question is if it will be connected.
Okay, never mind. I can do without it. I hope you can understand.
All right. Yeah.
When you showed what you call the radial model, bipartite graph.
Maybe it could work. But, okay.
There's a similar model, identical from your perspective, that exists in fiber optics.
Okay.
Where again, if you have fibers and in the middle what's called star couplers, where every light coming in on every fiber
thought I can do two things simultaneously, but eventually I cannot. All right, so if you...
what I'm basically what I'm about to do is add another consideration to this story, the second half of your thought, second part. And that is, if you have a bipartite graph, like the one you had on page 28, for example, but you implement it, okay, if you transmit power P at some transmitter, the received power will be P divided by the out degree of the transmission, obviously, but divided also by the in degree of the receiver, because of some physical phenomenon in the fiber optics. Now, the less power arrives, the slower the transmission. Not delay in terms of propagation, like you need a certain amount of energy per bit to tell it light or dark. So, if the product of out degree times max out degree, in degree along the path is larger, you have to slow down your transmission if you use the same power.
So it's good for me that at least one of them will be smaller.
So what you would actually want to do is somehow avoid the situation for a given bipartite graph in which obviously the net out degree has to be whatever the number of receivers you need to reach. The net in degree is also given. It is the number of transmitters you need to hear. But sometimes I can implement it, embed it in a graph that is multi-stage, combining the out degree and in degree. For example, if everyone needs to reach everyone, instead of saying first fan out and then fan in, I can say let's go into an n by n coupler, so I lose only a factor of n, nothing squared. Now, the relationship is, first of all, it's interesting when you get to design the graph to take this into consideration. Also, when you slow down transmission, it is different than what you call delay. What you call delay meant that if I transmit at time 1, it will occupy the receiver only for one time slot sometime later. In the meantime, it can receive other things. When I transmit more slowly, it will occupy the receiver for a longer amount of time. So it's taxing you more heavily. So it's just another degree of problems.
I understand.
For the special case that we considered in that 93 paper, we were able to construct, I was able to construct the bipartite graph as a multi-stage that is efficient. So I didn't lose power. But in general, it's a very complex problem.
So in general, you mean not for the complete bipartite graph, but for a general graph?
Yeah, and it may influence the graph that you want to, you may want to pay in some place. And
Yeah, it might be interesting.
You spoke about induced matching. What about if you go away from the pure combinatorial problem and do something which is not exactly induced, like you allow for some percentage of disturbance between
It will not, so basically it will not change it by much, because somehow if a graph is, depends, if a graph is close to being an induced matching in the sense that, for example, the maximum degree in it is small, let's say 2 or 3 or 5, then you can split it into not too many induced matchings. So maybe it will not change by much. But again, it will depend how the precise definition of the disturbance will be. It will be able to say something.
About the construction of the almost complete graph. So, I mean, is it so that you cannot really get complete graph or really near complete graph?
Yeah, well, you cannot get complete graph because the complete graph does not have an induced matching of size 2.
No, but you have many matches.
No, but you want it to be induced in the graph, right? But it is true that you can ask, and we're looking at that, so you can ask for lower bounds. So how good is the error term? So how many edges? So for example, you can show that if you use matchings of size 2, really matchings of size 2, then you must, the number of missing edges that you will not be able to cover is at least n to the 3 halves. And this was sharp, I think. I don't remember if it was. is maybe in the bipartite version, not in, at least in one version, for sure. And, but in general, there is a pretty big gap, but there is some lower bound on how many edges you have to miss if every matching is of size R. So,
and in this construction, you said that it's a simple construction, so you can actually give the construction is just a proof in digital?
Yeah, I can tell you the graph. There are two things, right? There is a graph, and then there are the induced matches. So here is a simple construction of the graph. So you take C will be some big constant, integer, and you take all the vectors of length n with coordinates in 1 up to C. It's like but you think about them as they lie in the Euclidean space, let's say. So these are points in the Euclidean space. Then there is a typical Euclidean distance or square distance between two random points. You take two random points in this set, you ask what is the typical Euclidean distance.
The most common distance.
Yeah, let's say the most common or the average, or so let's call it mu. Now, the graph. Euclidean distance, yeah, it's important. This is Euclidean distance. And now 2 will be adjacent even only if the distance between them is pretty close to mu. Okay, and because in high dimension
pretty close is what? Constant?
Okay, so the square distance differs from u squared by at most n, the dimension, let's say. These are the parameters we use, but it's not so crucial. I mean, the important thing is that because the dimension is high, so n will be big, then the distance between almost every pair is roughly is very close to the typical distance, and because of this, almost every pair will be connected, right? Because
this is the measure concentration.
right, so that's just the measure concentration. So this is the graph. Now you have to show where the induced matches are coming from, and that's another geometric thing. And there is some